Ask anyone to name Earth's longest mountain range, and you'll hear the Andes. But the Andes are just over 4,000 miles long. There is a hidden range almost 10 times that length, wrapping the planet for 40,389 miles and covering nearly a quarter of the Earth's surface. Yet 99% of us will never see it because it is buried beneath 2 kilometers of ocean. For decades, scientists insisted the seafloor was flat, a lifeless plain. Then, World War II sonar shattered that myth, and what they found turned geology upside down. How could something so colossal remain invisible? The answer starts with the greatest misconception in ocean history. For most of the 20th century, the ocean was thought of as little more than a giant, water-filled basin. Textbooks described the seafloor as a flat, featureless plain covered in endless mud, quiet, unchanging, and utterly dull. Scientists pictured the ocean bottom as the world's biggest bathtub, its only purpose to collect water that had gathered over billions of years. The idea was so firmly rooted that it shaped generations of research and exploration. Maps showed nothing but blue, with an unbroken level floor hidden beneath the waves. In 1912, a German meteorologist named Alfred Wegener challenged this vision with a radical idea: continents move. He pointed to the way South America and Africa seemed to fit together and argued that the continents had once been joined, slowly drifting apart over time. But Wegener's theory of continental drift ran headlong into the physics of his day. Geologists and physicists dismissed him outright. The problem was friction. The ocean floor, they insisted, was solid rock. There was no way entire continents could bulldoze their way through such resistance. Calculations showed the force required would be impossibly large. Without a mechanism to move continents, Wegener's theory was branded as fantasy, an interesting puzzle with no solution. For the next 40 years, the scientific world treated the idea as a dead end. The result was a quiet consensus. The ocean floor was flat, motionless, and ancient. The continents sat anchored in place, separated by an empty, unremarkable expanse. No one expected to find anything different, and no one bothered to look. It would take a global war and a burst of new technology to finally break open the bathtub myth. Until then, the greatest mountain range on Earth remained hidden in plain sight, waiting for someone to ask the right question. In 1942, the world's navies had a problem. Submarines were vanishing into the deep, and the only way to find them was to understand the ocean floor itself. The U.S. Navy began outfitting ships with echo sounders, machines that sent pings of sound into the depths and timed their return. Every journey meant miles of paper rolling out from the machines, each line tracing the rise and fall of the seafloor below. What started as a hunt for enemy U-boats became a revelation. Instead of endless mud, the echo sounders showed sharp peaks, deep valleys, and entire mountain chains where no one had imagined them. Fathograms, the scrolling sonar records, captured jagged lines and sudden spikes where the bottom shot upward hundreds or even thousands of meters. Sailors and officers who expected a flat plain found themselves staring at underwater cliffs, ridges, and chasms. Some of these ridges stretched for hundreds of miles, running straight through the Atlantic and Pacific like hidden backbones. The Navy's hydrographic survey ships, like the Pathfinder and the Sumner, logged thousands of miles of these traces, each new line adding to the growing sense that the ocean floor was anything but simple. These discoveries were not just academic. A submarine hiding in a trench or behind a seamount could evade sonar and slip away undetected. Accurate charts became a matter of survival. The urgency of war drove the mapping effort to a scale never seen before. By the end of World War II, the Navy had amassed a trove of data, continuous depth profiles, detailed logs, and fathograms that would soon find their way to civilian scientists. The old myth of a flat, featureless ocean floor had been swept away by the relentless pulse of sonar, leaving behind a mystery that demanded explanation. The ocean, once thought to be a static basin, was suddenly alive with hidden landscapes, waiting for someone to decode the patterns buried in all those miles of paper and ink. In the early 1950s, the basement of Columbia University's Lamont Doherty Earth Observatory was a world apart from the open decks of research ships. Down here, Marie Tharp worked alone, surrounded by stacks of sonar rolls and the constant hum of fluorescent lights. She was not allowed on the ships that collected the data. Women were considered a distraction, or worse, bad luck. Instead, the echoes of the Atlantic Ocean arrived to her as endless paper traces, each one a coded message from a world no one had ever seen. Every roll of paper was a journey across the ocean, a thin black line rising and falling with the sea floor. Tharp's job was to make sense of these lines. She would stretch the rolls across her desk, smoothing them flat, and begin the slow process of translating jagged marks into profiles of the ocean bottom. It was painstaking work, measuring, charting, and redrawing by hand. For each Atlantic crossing, she traced the depth, plotting the highs and lows with a draftsman's precision. The process was slow, but it was also intimate. Tharp knew every dip and spike by heart. Sonar became her language. Pattern recognition became her obsession. She noticed that time and again the depth would rise sharply, a mountain hidden under 2.5 kilometers of water. But at the very crest, something odd happened. The line did not just peak and fall away. It dipped sharply, forming a deep, narrow notch right at the summit. Tharp saw it once, then again, and then on nearly every profile that crossed the middle of the Atlantic. Each time the same signature appeared, a peak, then a sudden drop, like a wound splitting the mountain's spine. She began to overlay profiles, lining up the traces from different ships and different years. The pattern held. The V-shaped notch ran like a scar down the center of the range, stretching from the icy waters near Iceland to the equator and beyond. Tharp drew cross-sections by hand, pencil on tracing paper, stacking evidence line by line. The more she drew, the clearer it became. This was not a random feature or a trick of the instruments. It was real, and it was everywhere. The shape was familiar. Tharp had seen similar valleys in East Africa where the continent itself was pulling apart. But this was the middle of the Atlantic, not a rift on land. The textbooks said the ocean floor was old and stable, incapable of anything as dramatic as a rift valley. Yet the data refused to cooperate with the old story. No matter how many times she redrew the maps, the V-shaped chasm refused to disappear. Working in isolation, Tharp trusted her eyes and her method. She checked every calculation, redid every profile, and compared each new trace with the last. The evidence was undeniable. The floor of the Atlantic was not flat, not static, and not whole. It was split by a valley so deep and so regular that it could only mean one thing. The planet was tearing itself open beneath the sea. In that quiet basement, Marie Tharp had found the signature of a process no one else had dared to imagine. Bruce Heezen did not buy it. When Marie Tharp brought him her drawings, the V-shaped gash running down the middle of the Atlantic, he brushed it aside as girl talk. It sounded too much like Wegener's old, ridiculed idea that continents drifted apart. Heezen worried about his reputation, about sounding foolish in front of the old guard. He told Tharp to start over, to redraw the maps, so she did. Every time, the same deep notch appeared, steady, stubborn, undeniable. The rift would not vanish, no matter how many times she rechecked the numbers or retraced the lines. Heezen's skepticism was not just personal. It echoed the doubts of an entire field. For decades, geologists had dismissed any hint that the ocean floor could split open. But Tharp's evidence was relentless. Still, Heezen needed something more, something that would convince not just him, but the world. That proof arrived in the form of earthquakes. Lamont's files held a catalog of seismic events, pinpointed by ships and stations scattered around the globe. Tharp and Heezen decided to overlay those earthquake epicenters onto her Rift Valley map. matching each tremor's coordinates with the jagged line she had traced across the Atlantic. The result was immediate and electrifying. Every quake lined up along the rift, hugging the valley's path from pole to equator. The pattern was too precise to be a coincidence. The planet was not just cracked, it was active, restless, alive. Suddenly, the V-shaped notch was no longer a curiosity or a cartographer's error. It was the scar of a living wound, a place where the Earth's crust was pulling apart and new ocean floor was being born. The alignment of quakes with the Rift Valley turned skepticism into awe. This was not a relic of some ancient catastrophe frozen in time. It was a process happening right now, every day, beneath miles of water. Heezen could not ignore what the data shouted. The same feature Tharp had traced in lonely hours became the backbone of a new way of seeing the planet. The Rift Valley was real, and the earthquakes proved it was growing. Within a few years, these findings would shake the foundations of geology. Tharp's careful overlays and Heezen's reluctant acceptance forced scientists to reconsider everything they thought they knew about the ocean floor. The evidence was no longer a matter of opinion or tradition. It was written in the language of seismic waves and inked onto the very bones of the Earth. The ocean floor was not dead. It was in motion, and the world would have to catch up. Harry Hess, a Navy veteran turned geologist, had a habit of seeing patterns where others saw only isolated facts. In 1960, he published what he called an Essay in Geopoetry, a paper that challenged the very foundation of Earth science. Drawing on years of shipboard data and the detailed maps produced by Marie Tharp, Hess looked at the rift valleys and earthquake lines crisscrossing the ocean floor and saw a living system at work. Instead of viewing these features as ancient scars, he imagined them as evidence of an ongoing process shaping the planet beneath the waves. Hess proposed a radical idea. The ocean floor was not fixed or ancient, but constantly renewed. He pictured the seafloor as a conveyor belt, with new crust forming at the mid-ocean ridges, vast underwater mountain chains that spanned the globe. Here, hot magma surged upward from the Earth's mantle and reached the ridge. When it met the frigid ocean water, it cooled and solidified, creating fresh rock. This new crust did not remain in place. It pushed the older crust away from the ridge, spreading the seafloor outward in both directions. This process was unlike the mountain building that shaped the Rockies or the Himalayas, where continents collided and rock was forced upward. At the mid-ocean ridges, the new crust rose not from compression, but from buoyancy. The rock at the ridge was hot and less dense, so it floated higher above the seafloor, supported by the heat of the magma below. As it moved away from the ridge, it cooled, became denser, and slowly sank, forming the gentle slopes seen in sonar profiles. The entire ocean floor, Hess argued, was in motion, created at the ridges, pushed outward, and eventually destroyed elsewhere. Hess's model explained why oceanic crust was so much younger than the continents. If new crust was always being formed at the ridges, the old crust had to go somewhere. He pointed to the deep ocean trenches, long, narrow depressions at the edges of ocean basins. There, he suggested, the oceanic crust plunged back into the mantle in a process he called subduction. The seafloor was not permanent. It was born at the ridges, traveled thousands of miles, and finally disappeared into the depths, only for the cycle to begin again. Hess's conveyor belt model tied together Tharp's rift valleys, earthquake patterns, and the global network of trenches into a single, elegant mechanism. It offered a solution to the puzzle that had haunted continental drift, because continents did not need to bulldoze through solid rock. They rode along on the ever-renewing surface of the planet. By 1960, Hess's hypothesis had given geologists a new way to see the Earth. But bold ideas needed proof. Until then, the restless ocean floor remained a theory awaiting its evidence. On the chilly waters near Iceland in 1963, a British research vessel towed a magnetometer across the mid-Atlantic ridge. The instrument, designed to measure subtle changes in Earth's magnetic field, traced a path over the mountains and valleys mapped by Marie Tharp just a decade before. But this time, the focus was not on the shape of the seafloor, it was on the invisible, magnetic fingerprints locked inside the rock. Fred Vine and Drummond Matthews, two young geophysicists at Cambridge, pored over the magnetic data. What they saw was a pattern no one had expected, alternating bands of strong and weak magnetism, running parallel to the ridge, stretching for hundreds of miles. These were not random fluctuations. The stripes were crisp, regular, and most importantly, perfectly symmetrical on either side of the ridge's central axis. It was as if someone had painted a barcode across the ocean floor, with each stripe telling a story from deep time. The explanation lay in the nature of Earth's magnetic field. Every few 100,000 years, the planet's magnetic poles flip, north becomes south, and south becomes north. When molten lava erupts at the ridge and cools to form new crust, iron minerals within the rock act like tiny compass needles. They freeze in place, recording the direction of the magnetic field at that moment. As the seafloor spreads, these bands of rock are carried away from the ridge, preserving a record of every flip, normal, reversed, marching outward in both directions. The symmetry was the key. On the east side of the ridge, the sequence of magnetic stripes matched the sequence on the west, stripe for stripe, mile for mile. There was no way this could happen unless new crust was being created at the ridge and pushed outward, carrying its magnetic memory with it. The seafloor was acting as a giant tape recorder, capturing the planet's magnetic history as it grew. Vine and Matthews published their findings in Nature, and the effect was immediate. The mirrored stripes were the smoking gun. They provided the physical proof that Harry Hess's conveyor belt was not just a clever idea, it was happening right now beneath the ocean. The ocean floor was not fixed or ancient. It was being born at the ridges, recording the planet's magnetic reversals as it spread, and moving outward in a steady, unstoppable march. For the first time, the invisible processes shaping the planet had left a record that anyone could read. The magnetic stripes locked the theory of seafloor spreading into place, vindicating Wegener, Tharp, and Hess in one elegant, irrefutable sweep. The Earth's crust was on the move, and the evidence was written in stone, striped and mirrored beneath the waves. Mountains usually rise where plates collide, but the ocean's longest range is built by heat. At the center of a mid-ocean ridge, the crust is fresh from the mantle, hot, soft, and less dense than the cold, ancient seafloor far away. This difference in temperature and density is everything. It is buoyancy. Hot rock expands, making it lighter, so it floats higher on the mantle below. The result is a massive underwater swell, sometimes more than 2 kilometers above the abyssal plains on either side. The process starts deep underground. Magma wells up from the mantle at temperatures near 1,300 degrees Celsius. As soon as it hits the icy seawater, it cools and hardens, but it does not lose all its heat at once. The newborn crust stays warm for thousands of years, keeping its buoyancy. Like a raft on a lake, the hotter and lighter the crust, the higher it rides. That is why the crest of the ridge stands tall, while the flanks slope gently downward, getting denser and heavier as they cool. This is not a narrow peak. The ridge is a broad plateau, sometimes stretching dozens of miles across. The highest points are found at the ridge axis, where the crust is youngest and the heat is most intense. With every mile away from the center, the crust ages, contracts, and slowly sinks. Over millions of years, this steady cooling carves the classic profile of the ridge, a high central backbone dropping off into the deep. The scale is staggering. The ridge system rises up to 2,500 meters above the surrounding seafloor, with the entire structure shaped not by pressure from above, but by the relentless push of heat from below. This is mountain building by buoyancy, not by force, a process powered by the planet's internal engine. The mid-ocean ridge is not just a crack, it is a living, rising scar, floating on the heat that never stops escaping from Earth's core. A mid-ocean ridge is not a simple crack, it is a vast scar stretching for thousands of miles, and its shape is anything but straight. At the center, the Rift Valley slices through the ridge, a deep gash typically 10 to 20 miles wide. That is the distance from Manhattan to JFK Airport, or the width of a major city. This is where the crust is actively splitting, the literal boundary between two tectonic plates. The Rift Valley is not a neat line. It is broken, stepped, and jagged, with flanks that drop off steeply into the abyss. If you could strip away the water, you would see a canyon running the length of the Atlantic, its walls fractured by countless faults and landslides. But the rift does not run in a straight shot from pole to pole. The Earth is a sphere, so the ridge cannot follow a single path. Instead, it is segmented by a series of horizontal breaks called transform faults. These are not cracks that open up. They are fractures where the seafloor slides past itself, offsetting the ridge by dozens or even hundreds of miles at a time. Each segment of the ridge is displaced sideways, creating a zigzag pattern that, from above, looks like the teeth of a zipper. Some transform faults, like Romanche or Charlie Gibbs, are so large they can be traced for hundreds of kilometers, cutting across the seafloor like scars from an ancient wound. The result is a global mountain range that does not march in a straight line, but twists and turns to accommodate the roundness of the planet. This geometry is not an accident. It is a direct response to the way plates pull apart on a curved surface. Each offset, each jagged step, is a record of how the planet's skin is being torn and stitched back together. The Rift Valley and its zipper faults are the blueprint of a restless Earth, a living map of the forces that shape the ocean basins and ultimately the continents themselves. Not all mid-ocean ridges are created equal. The speed at which the seafloor spreads changes everything: the shape of the mountains, the depth of the valleys, even the chemistry of the rocks. In the Atlantic, the Mid-Atlantic Ridge creeps open at a slow pace, about 2 to 5 centimeters per year. That is the speed your fingernails grow. Here, the crust has time to cool and crack. The result is dramatic. A deep, rugged rift valley splits the ridge, flanked by steep cliffs and jagged scarps. Earthquakes cluster along the valley, and the landscape is as rough as any found above the waves. A world away, the East Pacific Rise races ahead at up to 15 centimeters per year, more than 6 times faster than the Atlantic. This is the speed hair grows. The crust here barely has time to cool before it is shoved aside by the next pulse of magma. Instead of breaking and faulting, the hot, ductile rock bulges upward, forming a broad, smooth dome. There is no Grand Canyon at the crest, just a gentle rise, barely a valley at all. The entire ridge is lower and flatter, with fewer cliffs and less drama. At the far extreme lies the Gackel Ridge beneath the Arctic ice. There the plates drift apart at less than 1 centimeter per year. This is the slowest spreading ridge on Earth, a pace so sluggish that the mantle can barely keep up. Magma supply is thin. In some places the crust is so starved that raw mantle rock is pulled up to the surface without even melting. The landscape is stark, with wide valleys and exposed peridotite, a direct glimpse into Earth's deep interior. Each of these ridges, slow, fast, and ultra-slow, tells a different story about the energy flowing from the planet's core. The speed of spreading leaves its fingerprint on the seafloor, shaping mountains that most of us will never see, but that define the hidden architecture of our world. In February 1977, the deep-sea submersible Alvin slipped beneath the surface of the Pacific, carrying a small crew of scientists toward the Galapagos Rift. Their mission was to investigate a problem that had stumped geophysicists for years. The numbers did not add up. The planet was losing heat, but not nearly as fast as it should have been. The mid-ocean ridges were supposed to be cooling the Earth, yet calculations showed a missing piece, an invisible escape route for all that energy. Alvin's lights cut through the darkness 2.5 kilometers down. The crew expected to find a wasteland of bare rock and mud. Instead, they found towers rising from the sea floor, belching thick black smokers into the water. These were the first hydrothermal vents, later called black smokers. The water erupting from them was superheated, reaching 400 degrees Celsius, hot enough to melt lead. But the immense pressure at this depth kept it from boiling away. The vents blasted out mineral-rich fluids, staining the water with clouds of iron and sulfur. As the hot water hit the cold ocean, dissolved metals precipitated out, building twisted chimneys that grew taller with every surge. The real shock came when the crew looked closer. Life was everywhere. Clusters of giant tube worms, some over 2 meters long, ringed the vents like pale sentinels. These creatures had no mouths, no digestive tracts, just a red plume that waved in the current. Nearby, pale crabs scuttled over rocks, and shrimp with no eyes clustered in the warm flow. Bacterial mats coated the stones in a living carpet. This ecosystem was unlike anything seen before. It did not depend on sunlight. Instead, bacteria deep in the tube worm's tissues used hydrogen sulfide from the vent fluids as fuel, turning chemicals into energy, a process called chemosynthesis. The discovery rewrote the rules of biology. Here, in the pitch-black depths, life thrived on the heat and chemistry of a planet that was still alive inside. The missing heat was not lost. It was powering entire worlds, hidden in the dark, at the base of Earth's longest mountain range. Beneath every ocean, a 40,000-mile mountain chain still reshapes our planet, right now, at the speed your fingernails grow. This relentless force builds continents, triggers earthquakes, and fuels ecosystems where sunlight never reaches. As climate shifts and ocean chemistry changes, the ridge's restless engine will echo in our future. Earth's greatest frontier isn't out of sight, it's still in motion, beneath our feet. What would the world look like if we mapped every hidden frontier?